Today we start on important topics related to left multiplication transformation. Okay, we also that means discuss in earlier in previous class also. Okay, but we start from definition today. Left multiplication transformation. Okay. This one. Now we write here let A be an M cross N matrix. Okay, with entries from a field. With entries from a field A. From a field A. Okay. Then we define. We define. Okay. We define by LA. LA. The mapping LA. The mapping LA such that here Fn to Fn defined by okay LAX equal to AX. Okay, the, the product of matrix A and X for each column vector for each column vector X belongs to F. Understood? Then LA is called. Then LA is called the left multiplication transformation. Okay. We also give this example and further discussion on theorem in previous class. But today I just discuss this definition. Okay. And now we're going to another theorem related to matrices. Okay. We write it here. Let A, B, C, A, B, and C. Okay. Be matrices such that such that A of BC is defined okay, then AB of C is also defined okay, and A of BC equal to AB of C. Understood? That is matrix multiplication is associative. That is matrix multiplication is associative. Understood? Now we're going to prove of that. So erase our portion. I'm going to prove of that. So here we write in this way. Here L A B C. Sorry, L A B C equal to what? Equal to we know about that L A and B C. Okay. Equal to what? Equal to L A L of B L of C equal to what? Equal to L A L B L C equal to what? Equal to L of AB, L of C equal to what? Equal to L of ABC. Okay. Then what happened? Then we get A of BC equal to AB of C. Understood? Not a problem at all. We also discuss this one too easily. Now so going to discuss and then we also prove matrix multiplication is associative. This one is proved now. Okay. So we're going to definition of the means an incidence matrix. Okay. We also write this one. We erase this portion and going to further discussion of that. Here we talk about that a large and varied collection of inters, in, interesting applications arise in connection with special matrices called indices matrices. An indices matrix and an incidence matrix. Okay, an incidence matrix is a square matrix. Is a square matrix. Okay, is a square matrix and obviously in which all the entries are either 0 or 1, in which all the entries are either 0 or 1. Understood? And then what happened? And all diagonal entries are 0, and obviously all diagonal entries are 0. And another way we discuss incident matrix and sum of rows equal to 1 and sum of this one obviously one type of matrices, but we discuss not now here. Okay, just incidence matrix, that means in which all entries are either 0 or 1 and all diagonals are 0. Okay, so we give another example here. Okay, then also write it in this way, that means aij equal to 1 if I can send a message, okay, to J, and aij equal to 0 otherwise. Okay, now also going to discussion another, that means here another, that means matrices we write it here now 0 1 0 1 1 0 1 1, here 0 0 0 0 and 0 1 1 0. Okay, this one be an incidence matrix. Okay, so this is one type of incident matrix. Okay, then also going to in generally discussion about that. That means if we do a square, okay, then some square equal to a square is not become an incident matrix. Okay, this one is possible and obviously in general mm, a plus a square a to the power m as is the number of ways in which I can send j in at most 10 stage. Okay, but this one is not discussed now, and another way we also discuss another definition. Okay, yeah, that means a clique. Okay, a clique we discuss now. A maximal collection, a maximal collection, a maximal collection of three or more people, of three or more people, or more people. Okay, with the property that, with the property that, with the property that, okay, any two can send to each other. With the property that any two can send, any two, okay, can send to each other, can send to each other, is called a clique. Is called is called a clique. Understood? Then we're also going to discuss another property of clique, which is our portion. Okay, this one, if P, that means a new matrix B, here Bij equal to 1. Okay, if I and C can send to each other, if I and J can send messages to each other, to each other, okay, and others one are 0 and others one Bij 0 otherwise, okay, then what happened? Also a matrix B, this one satisfies, then what happened is here. Okay, then obviously we say about that the person I belongs to a clique. Okay, person I belongs to a clique. When this one is happen, if and only if and only if PQII is greater than 0. Understood? Then we are also going to discussion of one example, okay, related to that topics. So here is your portion. I'm going to further discussion of that. So we write here a equal to what? A equal to 0 1 1 1 1 0 1 1 0 1 0 0, okay, and 1 0 1 0. Then what happened? Then to determine which people belong to clique, we form the matrix B described earlier. That means B equal to in this way. Okay, 0 1 0 1. Okay, and again 1 0 1 0 and 0 1 0 1. Okay, and here 1 0 1 0. That means this. Okay, here this one with respect to this one with respect to it, and this one with respect to this connection, and this. All are connected. Okay, that means if one to send messages, then to one of those will send messages. So here one. In this way, we also form one B. This satisfy clique. Okay. Then what happened? Then we also going to check about that BQ equal to what we get 0 4 0 and 4 0 0 4 0. Okay, 0 4 0 4 4 0 4 0. In this way BQ equal to, okay, since all diagonals of BQ are 0. Okay, yeah, all diagonals of BQ are 0, so there is no clique in this case. Okay, so that means all diagonals of PQ is 0. So so there are no clique in this relationship. There are no clique in this relationship. Understood? That means PQII. That means diagonal of PQ are greater than 0, then this one is done. But here this one is not done. Okay. In this way, we also going to discuss on dominance relation. Okay. We also going to discuss on dominance relation. So it is that portion now. Here we write a dominance relation. A dominance relation. Okay. What happened is here. A relation among a group of people is called dominance relation. A relation among a group of people, a group of people is called a dominance relation. Okay. If the associated okay, associated incidence matrix, okay, A has the property that A has the property that okay, A has the property that for all distinct pairs I and C, okay, for all distinct pairs I and C, Aij equal to 1 if and only if Aji equal to 0. Okay, that means any two people exactly one of them dominates. Okay, the other. So we write it in that means short. This one is how much? That means in any two people, okay, any two people, exactly one of them dominates. Exactly one of them dominates. Okay, understood? Exactly one of them dominates the other. Dominates the other. Okay, not a problem at all. Now, so since A is an incident matrix, so AII equal to 0 for all I, then A plus A square has a new row in which each entry is positive except for the diagonal entry. Okay, and obviously this matrix to a dominance relation, We now also discuss one example in this way. A equal to here. Okay. 0 1. Okay. 0 1 means here 0 and 0. Okay, this one is a dominant series because here the diagonal are 0, not a problem at all, and obviously here one also send message to 2 but 2 not send message to 1. Okay, then this one is an, that means dominance relation. Okay, this from a dominance relation, understood. And then we check, that means a plus a square equal to 1. A plus a square equal to a equal to 0 1 0 1 and a square equal to 0 0 0 0. Okay, then what happened? Same a. Here a square equal to 0, so this one is obviously, that means dA be satisfy a dominant relation. Okay, that means a square plus a square equal to a. Okay, here a plus a square equal to a, and obviously this one satisfies dominant relation. So we write it, for such a relation a plus a square has a row in which each entry is positive except for the diagonal entry. Okay, but this one is not satisfied here. Okay, that means ai is 0, and obviously for such a relation, okay, the matrix a plus a square has a row in which each entry is positive. Obviously here has a row, each entry positive, this row, okay, except the diagonal. This one happened. Okay, so this one is a criteria. We write it now. We erase that portion, and criteria of dominance relation. So we write it in lower portion. Criteria is what? That means in this way we write it. Mm, since A is incidence matrix, incident matrix. So what happened? So AI equal to 0 for all I, for all I. Okay, and for such a relation, for such a relation, for such a relation, what happened? That means the matrix A plus A square, the matrix A plus A square, okay, has a row, has a row in which, has a row in which, okay, each entry is positive, in which each entry is positive except for the diagonal entry, except for the diagonal entry. Okay, a row has a row in which each entry is positive. Okay, this one that means criteria of dominance relation. Okay, so today we discuss this one too easily, and obviously we discuss some trace of matrices, and obviously discuss some property of trace of matrices. Now we erase that portion and going to discussion of some trace of a matrix. Okay, we know about that trace of matrix, and now we're going to discussion of that trace of, trace of a matrix. Okay, yeah, we write it in this way. Let A be n cross n matrices. Okay, n cross n matrices. The trace of A, the trace of A is defined by, is defined by trace of A equal to summation I equal to 1 to AII. Okay, then we have to prove that, then we have to show that what, so that trace of AB equal to trace of EA. Understood? And trace of A equal to trace of A transpose. Okay, not a problem at all. So we now discuss here trace of AB equal to trace of BA. How we done so? Here we know that trace of AB equal to what? Trace of AB equal to summation I equal to 1 to n. Okay, I equal to 1 to n. Here AII and BII. Okay, and then this one is, that is how we obtain in this way, and trace of BA equal to what? Here I equal to 1 to n BII. This one we know that AII BII equal to BII. So what happened? So trace of AB equal to trace of EA. Understood? Not a problem at all. And then we are also going to discussion of that trace of A transpose equal to what? Trace of A transpose equal to summation I equal to 1 to n AII transpose equal to summation I equal to 1 to n AII equal to trace of A. Okay. So in this way we discuss trace of some property of trace. Okay, and to easily to prove this one, trace of AB equal to trace of BA, trace of A equal to trace of A transpose. We also prove this one. Okay. Now today we also, that means, satisfies another a problem related to dominance relation. So it is that portion and going to further discussion of that. So here the matrix the matrix A equal to 0 0 1 1 0 0 0 1 0. Okay, this one corresponds to a corresponds to a dominance relation, to a dominance relation. Okay, correspond to a dominant relation. How this one happen? We write A equal to 0 1 0 0 0 1 1 0 0. Then this one here 0. Okay, this one here 0, and this one and here 0, and other diagonal are 0. So this one being dominant relation. So how we write this one? Okay, we write it since AII are 0, so AB and incidence matrix. Understood? Next, we talk about that Aij equal to 0 if if Aij equal to 1 if I can say j, but j, if I can send message to j. Okay, I can send message to j, but j can't not reply. Okay, but say that means here aij equal to 0. I can send message j and aji equal to 0. That means uh, here j can't reply I. Okay, in this way, also they satisfy this a is satisfied here. That means aij equal to 1 and aji equal to 0. Okay, that means any two people exactly one of them dominates. Okay, any two people given any two people given any two people exactly one of them dominates. Okay, exactly one of them dominates. Not a problem at all. This one happened, and again we also see about that. This one is done, but we also check another property. Okay, this property is too easily. So A satisfies dominant relation, but this property is what we write it in this way: A square equal to what? 0 1 0 0 0 1 1 0 0. Okay, yeah, 0 1 0 0 0 1 1 0 0. Then a square equal to what? Yeah, 0 0 1. Sorry, is this one is right. Here 1 0 0. Okay, here 0 1 0. Then a plus a square equal to what? A 0 1 0 0 0 1 1 0 0 plus here a square 0 0 1 1 0 0 0 1 0 equal to what? 0 1 1. Understood? Here 1 0 1. Here 1 1 0. That means a square plus a square. Okay. Have this one a square a plus a square. Okay, have a row in which each entry is positive. Have a row in which each entry be positive, be positive. Okay, this row otherwise diagonal all are positive. Okay, positive except for diagonal, except for diagonal end. Understood? Then what happened? Then we see that this one is a satisfies satisfies dominance relation. Dominance relation. Understood? A satisfies dominance relation. So today I'll stop here. If you get this type of videos, please subscribe my channel and follow this video. Okay, see this video. That means in a proper way and regularly see this video. And obviously, if you want to give like, please click on like options. If you have any questions, comments, suggestions, write it in comment box. So today I stop here. Thank you.